So in this video, we're going to talk about the Pythagorean Theorem, and specifically, we are going to look at how do you prove that the Pythagorean Theorem is true. So this is something you've used a lot in the past, but we just kind of accepted it because somebody told us so. So how do we actually prove the Pythagorean Theorem is true? There are actually a few hundred proofs of the Pythagorean Theorem that are all different. One of those proofs was even created by President Garfield, if you know anything about President Garfield. Anyway, there are 367 proofs that we know of, probably more. I've actually posted on Google Classroom a list of about 100 or so of them. They're all pretty visual, they're kind of cool, so if you want to skim through those, you can. We're going to talk about just a couple of them. So a lot of these proofs do include pictures, those are kind of helpful, but pictures are not necessarily enough. There's not necessarily a right way to prove something, there's usually an easier way to prove it or a shorter way, but as long as you start with stuff that is accepted as true and you do some sort of justification with it and you land with, okay, as long as I end up with a squared plus b squared equals c squared in this right triangle, then I've proved it. Note that it doesn't have to be called A, B, and C. I could call these whatever I want as long as it represents the short leg, the long leg of a right triangle, and the hypotenuse of a right triangle. So typically you'll see these proofs involve generic variables because we want it to stand for any right triangle rather than specific numbers. So that's why we use letters instead. Okay, so I do want to point out something about the Pythagorean Theorem, which is cool. When we say a squared, it literally makes a square. Like a squared is a square. It's a square where it's like a by a. A times a is a squared. So the area of this squared is a squared. The area of this square, if it was a square that is b by b, would be b squared. And if we made a square out of the hypotenuse c, c times c would be c squared. And literally, if you compare this area plus this area, it equals this area. That only works for right triangles, but that's still pretty cool. Like if I were to make squares out of it, like literally there would be the same number. For example, like 3 squared plus 4 squared equals 5 squared. If you make a 3 by 3 square and a 4 by 4 square, and you count up all the little areas, this plus this is 25, which is 5 squared. It's kind of cool. Okay, so here is one of my personal favorite ways to prove the Pythagorean Theorem, one of, hundreds. I'm going to start with a right triangle where I've got the legs labeled A and B, the hypotenuse labeled C, and I've actually got 4 of them laid out to where it makes a square. Okay, so that's just kind of what I'm going to start with. By the time I'm done, I want to get to, so a squared plus b squared equals c squared. I can't do that yet, but here's what I do know. I know that for the big square, I know that on this big square here, the length of the square is a plus b. So one side length is a plus b. And if I want to find the area of this big square, it would be a plus b times a plus b, or a plus b squared. Either way. So that's the area of the big square. I could also find the area of this little square here. So the little square, as you see, the area there is c squared. C times c is c squared. And then for one of these triangles, the area of a triangle is 1/2 base times height. So the base of the triangle could be b and the height could be a. So 1/2 b times a, or a times b. That is the area of a little triangle. All the triangles should be the same, and I have 4 of them. So here's an equation that I could come up with. if I added up all 4 triangles plus the little square, that should equal the big square. So I'm going to put that into an equation. C squared plus 4 of these triangles equals this. I'm going to go ahead and distribute this out, by the way. A times A is A squared. A times B is AB. B times A is also AB. And B times B is B squared. So if I combine these two like terms, that would be A squared plus 2AB plus B squared. So all of this adds up to be the big square, which is A squared plus 2AB plus B squared. You may start to notice that this is looking actually kind of similar to the Pythagorean Theorem. I've got C squared, I've got A squared and B squared, but I do have a little bit of some extra stuff. So let's simplify just a little bit and you watch what happens. 4 times a half is 2AB. So I've got C squared plus 2AB equals A squared plus 2AB plus B squared. And I'm pretty much done. Because if I subtract 2AB from both sides, that cancels. And I'm left with A squared plus B squared equals C squared. So I'm done. Put a little square, a little QED. I'm done with my proof. This work kind of proved it, along with that diagram. Okay, so that's one proof. Another one that's pretty similar is instead of having the triangles all on the edges, you could have the triangles kind of pushed together. And you could come up with the area for this little thing and this little thing and these 2 separate ones. And again, set it equal to the big square. And once you do some calculations, you'll get down once again to A squared plus B squared equals C squared. Again, there are hundreds, but I just think that's kind of cool that we proved it. Okay. The proof that we are going to focus on in this unit is a little more complicated than that, if I'm being honest. But the reason we're focusing on it now in this unit is because this proof has to do with similar triangles. It has to do with what we just did. So for this proof, I'm going to start off with a right triangle, again labeled A, B, and C. And by the time I'm done, once again, I want to have A squared plus B squared equals C squared. That's my goal. To start off with, I have a challenge for you, which is, could you create 3 similar right triangles out of this one by just drawing one straight line segment? So take a second and see if you can try that. All right, hopefully you've tried it. I'm going to go ahead and ruin the secret. The way you could create it is if you dropped a perpendicular line from this corner down to the hypotenuse at a right angle. And so we need to talk about why these are similar. So now go ahead and think to yourself, why do you think that those triangles, and here's a better picture, why do you think this triangle, and the big triangle, why do you think that those are similar triangles? And remember, it's going to be one of 3 properties, either side, 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 angle, or angle, angle. I don't really know anything about the side links at the moment. All I've done is give them names. I don't know what those relationships are, but I do know something about the angles. The first thing I know is that they all have a 90-degree angle. The big triangle has this 90-degree angle. The medium triangle has that 90-degree angle. And this little triangle has this 90-degree angle. So they all share a 90-degree angle. But I have to have another pair of angles to make them similar. And I actually have that as well, because you'll notice this angle right here is shared by the big one and the little one. So they share that angle. And then this angle right here is shared by the big one and the medium one. And so those 2 are similar as well. And so the reason I know all of these triangles are similar is because of angle, angle. Okay, so basically what we're going to do is, there is an overview of the proof. We're going to say they're similar because of angle-angle. We're going to set up some proportions with the sides like we normally do with similar triangles, do a little cross multiplying, and by the time we're done, we'll have a squared plus b squared equals c squared. Okay, so I'm going to go ahead and break up the triangles for us because I think this is going to help. So this little triangle here, I kind of flipped to be facing the same way, and this medium triangle I also kind of reflected over here so that they're all 90, 90, 90 and they kind of line up and it's easier to see. But just to be clear, this came from here, that came from here, and then we've got the big triangle as well. Okay, so the first part of this proof is to say, okay, well, angle ABC is congruent to angle ACB, which is congruent to angle CDB. That's because they're all right angles. I also know that this angle right here, angle CAB, is congruent to the little triangle, DAC, because it was there at the same spot. And so they share that one, and so I know that these two are congruent with or similar with angle-angle. And then again, I can do the same thing with this angle and this angle because it came from the same spot. So I know that angle ABC is congruent to angle CBD. And that's because they share that angle. And so now I know that triangle, I'm just going to write all three triangles. So all three triangles are similar. And the reason I know that, again, is because of angle-angle. Okay, so that would be the first part of this proof. I'm going to go ahead and erase that. And we're going to go on from here. So now that I know they're similar, I know that all the sides are proportional. So here's what I'm going to do. I know that the big triangle, I'm going to start by comparing the big triangle to the medium triangle. So I'm going to go big to medium. Now let's do this. Big and medium. Okay, so I know on the big triangle, its hypotenuse is C. And I know on the medium triangle, the hypotenuse is A. So this was the hypotenuse for both. And if we look at the long leg for both, I know that this one has a long leg of A, and this one has a long leg of, we haven't given that a name yet. It would be just this little section here, just this. I'm going to call it, just to give it a name, Y. And so we'll call this Y, because that's where it came from. Okay, so there's one proportion that I could set up. Let's do one more using the big and the small triangle. Again, we'll look at the hypotenuse. So the hypotenuse of the big one was C. The hypotenuse of the small one is B. This time let's look at the short leg. So the short leg on this big triangle was B. The short leg on the small triangle, again, doesn't have a name yet. I'm just going to call it X. Basically, I'm relabeling this as X and Y. Okay, I know that feels like I have a lot of variables, but I promise we're going to get there. So all I've done is just set up a couple proportions since they were similar triangles. And now, let's do a little cross multiplying and see what happens. So, if I cross multiply here, I get A times A, which is A squared, equals equals CY.
Teacher, sorry to interruption, but at this time, if you could release all softball players. Thank you.
And if I cross multiply on this one, I get B squared equals CX. You may start seeing some stuff that we need here, like A squared and B squared. It would be helpful if those were together. So what I'm actually going to do is just add up these two equations. So I've got B squared equals CX and A squared equals CY, and I'm going to add those together. Basically, I'm taking this equation and adding the same thing to both sides. Like, if I add A squared here, and this is equal to A squared, so if I add it here, that's the property of equality. I'm not changing the equation because I'm adding the same thing to both sides. So A squared plus B squared is just A squared plus B squared. We're almost there. And CX plus CY is CX plus CY. The reason we were allowed to do that is, like I just mentioned, that is the addition property of equality. So the addition property of equality says as long as you do the same thing to both sides of the equation, it's a legal move. All right, I'm going to go on to the next page. We've got A squared plus B squared equals CX plus CY. So wouldn't it be nice? Well, first thing I'm going to do is, let's go ahead and factor out that C. See how they both have a C? It's a GCF. So bring that C out to the front, leaving X plus Y left over, factoring out that C. We are so close to A squared plus B squared equals C squared. It would be really nice if instead of this, I had a C, because then I'd have C times C, C squared. And we actually do, because X plus Y is literally C. Remember, that's how I had designed it. This was X, this was Y, X plus Y is C. We call that segment addition because, like, if you add up two segments and get the whole segment, there you go. So I can replace this with a C because of segment addition. When you add up segments, you get another segment. And now we're done. So A squared plus B squared equals C squared. The reason for this step is C times C gives you C squared. Technically that's called the product of powers, because when you add up like C to the first plus C to the first, it gives you 2. So it's the product of 2 powers. And that is the end of my proof. A little QED, or put a square. The reason for this step, by the way, was I factored out the C, and so technically that's the distributive property, just by the way. Because I could distribute the C and get back to this. Okay, I know that's a lot, and the A, B, and C may not be called A, B, and C. For example, I'm going to have you guys practice this by basically starting with this triangle and filling in the reasons. And it's going to be a bit of a challenge because it's not called A, B, and C anymore. It's called PR, RQ, and QP. But it's the same proof and the same reasons. It didn't change at all. It's just labeled a little differently. So I know that could be a little confusing, but it is cool that this is one of the proofs that uses similar triangles.